Welcome into Calc 3. Today we are going over double integration with polar coordinates, right? Last video was Cartesian, now we're doing polar. As a reminder from Calculus 2 or before, x is equal to r cosine of theta, y is equal to r sine of theta, and x squared plus y squared is equal to r squared, right? So again, let's compare and contrast here. We were using double integrals to go from, we have Cartesian coordinates first. So we'll write this as f of xy dA over some region, let's just say. Right, now what we want to do is switch this to polar. So we know what x and y are equal to based on our polar coordinates. So let's say this is going to be over some region. We're going to leave this for a second, but f is going to be instead, right, r cosine of theta, r sine of theta, and we'll still leave this as dA for right now. Okay, so notice our two variables here were x and y. Our two variables are now radius and theta, right? So that's what we're going to be integrating with respect to. However, right, it might be, right, our first thing that we might want to do is go this, and I'm going to cross this out. Right, our first thing that we might want to say was, well, dA must be equal to dr d theta, right? This is kind of very intuitive, you would think. However, this is not correct, right? So I'm going to X it out. That's not what we want to do, right? So what we need to reference is, well, what are we really making over here? So we have a couple graphs over here, right? So you can see we're integrating between two radius, or sometimes just one, right? With the other one being 0, but between two radius and two thetas, right? Alpha and beta over here. Now you'll notice that we're breaking these into infinitesimally small polar rectangles, right? So I'm going to draw one of these infinitesimally small polar rectangles over here. You can imagine, we'll use this space here. So let's say I have some angle, right? And I'm trying to get this polar rectangle. This is dA here, right? Right, this is this small, infinitesimally small polar rectangle, right? And now what's the tricky part here is this is definitely the infinitesimally small change of the radius. And so we call this dr, right? An infinitesimally small change of the radius. Now, this piece here, right, if we want to find area, we need to multiply this value times dr. This piece here is an arc length, right? So we need to know the equation of an arc length from way back when, where arc length is equal to s, right? So x is the arc length, is going to be equal to the radius times theta, right? Well, in our case, right, this is arc length. Well, in our case, the radius is the radius, right? That's not, this is the actual value. However, this theta is the infinitesimally small change in theta, right? So this thing here, this arc length is actually r d theta, right? So when it's time to find dA, what we're doing is we're multiplying these two values. So instead of dA just being equal to dr d theta, it's dA is actually equal to r dr d theta, right? So this other r appears. This is a very common thing that people forget. We need the r because, again, this is coming from the arc length that we have this r over here. Okay? So now when it's time to set up everything, let's write out what this would look like. We have the double integral, and we'll say, and again, it might depend on the ordering, but for right now, we'll leave it as such. We have alpha and beta, which are our angles, or our thetas that we're integrating with respect to. We have a and b, which are going to be two different radius. We have f of r cosine of theta and r sine of theta. And again, don't forget, instead of dA, we're writing r dr d theta, right? So feel free to watch that again. Again, when we're breaking this down, we're making these infinitesimally small areas. That's what we're calling dA here. Right, and then we're adding up all of those areas to get a volume. Now this area, when it's a polar rectangle, right, same kind of idea, we're multiplying the width times the height kind of idea. where this dr, right, is the infinitesimally small change in the radius going this way, And this arc length here is constructed using r, because this can be a certain distance away, times the infinitesimally small change in theta, d theta. Right, so multiplying these both together is how we get our dA over here. Right, so again, do not forget the r, very common mistake. Right, so again, just a very brief intro. We'll go through a few different examples, remind you of U sub. No integration by parts in this video, but hopefully you guys enjoy. Welcome into our first example. Right, you should see the question pop up somewhere down here. I've already written out the equation for us, so let's go ahead and get started. Before we deal with the bounds, I'm just first going to switch over the variables, right? So we have, this is going to be the double integral of, this will now be 5r cosine of theta, right, substituting out that x, minus 3r sine of theta, r dr d theta, right? Okay, so now one algebraic step, we got to put the r into the equation. We'll do that in a second. First, let's look at our bounds. So if we're looking at the question, it says we're bounded by the circle x squared plus y squared is equal to 4, which means our bounds for our radius, which we're doing first, is between 0 and 2, right? That is the circle with a radius of 2. For d theta, it says we're bounded by x is equal to 0, right? And y is equal to x. So if we sketch this out, what we'll see is this is going to be pi over 4. Let's see if we can fit this in here. And pi over 2, right? So the pi over 4 is the y is equal to x. The pi over 2 is x is equal to 0. All right, let's do a little bit more algebra just to distribute in the r. So we have the double integral again, pi over 2, pi over 4, we'll squeeze those in there, 2, 0, and this becomes 5r squared cosine of theta, we'll leave a bracket around it, minus 3r squared sine of theta. Dr d theta. So first we integrate with respect to r, right? Well, this is easy. This is just an r squared and r squared, right? So let's integrate with respect to r here. Let's see, I'll give myself a little bit more room here. We haven't dealt with the thetas yet, so we still need to write that out. We have dealt with the integration here. So this is now going to become 5 times, this is now going to be r cubed over 3, and cosine of theta is just a constant here hanging out, so we'll leave it alone. Same thing over here, minus, and what happens here? If we raise this to the third power, divide by 3, and multiply by 3, we're left with r cubed sine of theta, all between 2 and 0, d theta. Okay, so pause for a second. Right, so r cubed divided by 3, reverse power rule. I made the cancellation with what would have been the denominator in this 3, so we're left with just r cubed. So now we have to evaluate between 2 and 0. So let's plug in 2, we'll plug in 0. We have still pi over 2 and pi over 4. If I plug in 2 here, I'm going to get 2 cubed, 8 over 3 times 5. That is going to be the ugly 40 over 3 cosine of theta minus, this is just going to be 8 sine of theta. And now you're welcome to go plug in the 0, right? If I plug in 0 here, I'm going to get a 0 minus a 0, so we can save ourselves a little bit of room. We'll put d theta. So now we're with an integral, right, of just one variable. So hopefully we're a little bit more comfortable with this. Let's go ahead. Where does a positive cosine come from? We'll write it over here. So we have 40 over 3. A positive cosine comes from a positive sine. And a negative sine comes from a positive cosine. So we'll say, we'll just put the equal sign over here. And we still need to evaluate between, we have pi over 2 and pi over 4, right? So we do have a little bit more work to do here. Now, if I plug in pi over 2, let's see what happens. I might need to split this up into two pieces here. If I plug in pi over 2, I have 40 over 3. Sine of pi over 2 is going to be 1. Okay, well that's nice to work with. Plus cosine of pi over 2. So that's 0, right? Cosine of pi over 2 is going to be 0, so that's done. Minus, now what happens when we plug in pi over 4? Well, sine of pi over 4 is going to be rad 2 over 2, right? So 40 over 3 times rad 2 over 2. I might have to simplify this one on the fly here. Cosine of pi over 4 is also rad 2 over 2. So 8 times rad 2 over 2 is going to be 4 rad 2. We squeezed it in there. All right, so 8 times rad 2 over 2, 4 rad 2. Could have made the simplification here too, but that's okay. So let's see what we end up with. We have 40 over 3. That's good. That's done. Minus, let's simplify everything we have over here. So this is now going to be 40 and the 2 will make 20. So we have 20 rad 2 over 3 plus 4 rad 2. Now we need a common denominator here, so we'll make the common denominator 3. So this becomes 12 rad 2 over 3. And unfortunately, I think we're going to have to leave it as such, right? An ugly value of 40 over 3. Well, these are all going to be over 3 now, right? Right, this is over 3, that's over 3, they're all over 3. So 40 minus 20 plus 12, 32 rad 2. All over 3. And that is our final answer, regardless of it being ugly. So again, we had our integral. We had to convert this into polar coordinates. We have them over here as a reference, right? X is equal to r cosine of theta, y is equal to r sine of theta. This dA, remember, dA, don't forget here, dA is equal to r dr d theta, right? So we, right, distribute that r in. We have 5r squared, 3r squared. We integrate with respect to r, reverse power rule. We input the 2. We have an ugly fraction, at least we have a nice 8 there. Once we integrate with respect to theta, we jump over here, right? And we go through our simplifications of plugging in pi over 2 and pi over 4. So as usual, it is very useful to know the trig circle by memory, right? If you don't, make sure to practice it. This is one example. I will see you in the next one. Jumping into example 2. Now the problem should appear below. I've already written the integral out for us. So we are bounded between our first quadrant, right? So that's going to end up being 0 to pi over 2, as well as between two different radii, 1 and 3 here, right? So let's go ahead and start rewriting everything. So we have our double integral, and we're bounded between the first quadrant, so 0 to pi over 2, and we're going to be between two different radii here. We'll say 1 and 3. And now we have cosine of, well, x squared plus y squared. We know what that's equal to. That's r squared. And again, dA is equal to, don't forget the r dr d theta. Awesome. Okay, so let's pause for a moment. What type of integral is this? We're going to be integrating first with respect to r. So we might need to take a second. We've talked mostly about u sub and integration by parts. In this case, because of this r squared here, this is going to be a u sub. So let's go ahead and do a u sub here. We have u is equal to r squared, which means that du will be equal to 2r dr. However, what do we have? We have an r here, and we have a dr here. So let's just move the 2 to the other side. So we have 1/2 du is equal to r dr. Okay, now let's switch this integral right? So we're switching from R to U's. We're going to bring this 1/2 here all the way out to the front, right? So we have 1/2 integral from pi over 2 to 0. Let's see if I can write at this angle here. We're going to leave this one for right now. Or actually, let's switch the bounds as we go. Right, so if I plug in 3 for R, I'm going to get a U of 9. If I plug in 1, I'm going to get 1. Right, so I have my new U bounds. And now let's switch everything over. This ends up being cosine of U. And now we have a du, right, instead of a dr, and still the d theta. Good. Okay, we're going to jump over here. We should be fine with space-wise to do the rest of the calculation. So cosine of u, where does a positive cosine of u come from? It comes from a positive sign, right? So we still have our 1/2 hanging out here. We still have not touched our thetas, right? Pi over 2 and 0. We have integrated cosine to get sine of u between, right, so we're bracket this in for a second, between 9 and 1. And we still have the d theta, right? So we'll leave that there. So we end up with 1/2, let's simplify this out, pi over 2, 0. This ends up being a sine of 9, who knows what that is, minus sine of 1 d theta. Good. Now what is this entire thing? Well, this is a giant constant which we can move to the outside, right? So let's go ahead and do that. So we end up with, this is going to be a little bit ugly to write. We'll write it out as such. So we have sine of 9 minus sine of 1. This is a giant constant here, over 2 from the 1/2, right, previously. And now it's the integral of just, well, what's left over? Just 1 d theta, right? And we're still between pi over 2 and 0. So now if we integrate 1 d theta, what do we end up with? We just end up with a theta, right? So let's see. We still have this ugly constant that we have to keep writing over and over. All over 2. We'll have just enough room to evaluate. Right, this is going to be theta here between pi over 2 and 0. We know what 0 will evaluate to. So our final answer, right, you could plug in pi over 2 and subtract out 0. You're just going to get pi over 2 from this here. Right, so our final answer, the pi over 2, I'm going to swing the 2 over here. So we have pi times sine of 9 minus sine of 1 all over, and instead of 2, I'm going to put this other 2 here, so over 4, right, is our final answer. Awesome. All right, so again, take your time. This is a little bit of a, right, we added a little bit extra difficulty here because of the u substitution, right? X squared plus y squared is equal to r squared. We made that substitution. Again, I will mention it because someone will forget. Don't forget about this r here, right, coming from the arc length. So r dr d theta, we made our u substitution. Don't forget also to switch your bounds, right? So we switch from 3 and 1. If we plug them in, I get 9 and 1, right, in terms of u. Positive cosine, positive sine, we evaluated. We got an ugly number, but not too bad. So hopefully this is good. I will see you in the next example. Last example, right? So I've already set up the integral for you. The question should appear below, right? The main thing that we need to take away from the question after we've set up the integral is for finding the bounds, notice that x is equal to the square root of 4 minus y squared. What does that tell us, right? Well, one, that's going to tell us the radius is going to be 2, right? It also says we're bounded by a semicircle. Well, if we only have positive x values, right, what kind of semicircle do we have? Well, all the positive x values, we're going to have this half semicircle over here where we're bounded between negative pi over 2 and pi over 2, right? So we have all of our bounds just from that one piece of information. So let's go ahead and set this up, but as we do it, we're going to reconfigure some stuff. So let's actually do this first before we even go into polar, just so it becomes a little bit more obvious. This is e to the negative x squared plus y squared dA. All right, so now it's a little bit more obvious as to what we're supposed to do here. So let's go ahead. We're going to write our bounds. So again, the thetas we're between, because of the semicircle and positive x's, we are between negative pi over 2 to positive pi over 2, and our radius, because it's going x squared plus y squared is equal to 4, is going to be between 0 and 2. And now this is going to be e to the negative r squared. And again, what does dA translate to? Don't forget the r, right? R dr d theta. Awesome. Okay, so maybe pause the video, stare for a second. What is our next step? Well, our next step, right, what kind of problem is this? It's a u substitution problem, right? This r is going to get canceled out when we take the derivative of negative r squared, right? So our u here is u is equal to negative r squared, which means that du is equal to negative 2r dr. Now we have the r dr right here, but let's move over the negative 2. So this is negative 1/2 du is equal to r dr. So now we can substitute in a few times. Really quick before we jump to that side, what we also can do here is substitute out the r's, right? So if we plug in 0, well, that's easy enough. That's going to be 0. We'll just go over here. We'll do it. So let's rewrite our double integral with everything that we have now. Trying to make sure this lines up. We have now changed this, right? Negative pi over 2 to pi over 2. Now instead, right, if I plug in 0, I'm still going to get 0, so that's nice enough. However, if I plug in 2 squared 4, don't forget the negative sign, negative 4. And that makes sense because this negative 1/2 is going on the outside here, right? So even though this is going to evaluate to be something negative, when we multiply by a negative, we'll get a positive. So we're fine with that. We have e to u. And now this becomes a du. We still have the d theta. All right, now this looks fairly straightforward, right? Integral of e to the u. Correct, e to the u. This is still pi over 2 to negative pi over 2. And this is e to the u between negative 4 and 0, right? D theta. Awesome. If we plug in our 0, right, and our negative 4, let's see what we get. We have negative 1/2, still pi over 2 to negative pi over 2. If I plug in negative 4, e to the negative 4 minus e to the 0 is going to be 1 d theta. Now we'll pause here. What do we know about this? This is one giant constant. What can we do? We can move it out to the front. Now, I won't trick you here. Because this negative sign, I'm just going to flip these two, right? So the constant out in front is going to be 1 minus e to the negative 4 all over 2. Right, so the negative sign just flips that piece, and we're dividing by 2. And now we have the integral here of pi over 2 to negative pi over 2 of just 1 d theta. Let's see if we run out of room here. I think we'll be okay. I'll have to scoot down just a little bit. Right, if we evaluate this, this is just going to be theta. Right, so we end up with 1 minus e to the negative 4 over 2. And now this is evaluating theta from pi over 2 to negative pi over 2. And I'll pause here for a second because I don't want to shortcut this, but I might have to due to space. If I plug in pi over 2 and I subtracted negative pi over 2, I'm going to get a full pi. Right, so out of this here, this is going to evaluate to be pi. Right, so we can write our final answer now. And I apologize for skipping the one step, but feel free to go through the math right there. It should evaluate to pi. Right, again, pi over 2 minus a negative pi over 2, so pi over 2 plus pi over 2, pi. Right, 1 minus e to the negative 4 all over 2, and we are done. Right, so one more time, rewrite it. So we pull out the negative sign, x squared plus y squared, r squared, dA, always remember the r, don't forget. Right, we have a u substitution problem. We switch over our bounds, we switch over all of our u's, we evaluate, right? We can take this giant constant out to the front, and we're good to go, right? So real quick again, pi over 2 minus negative pi over 2, we get a full pi. Right, so hopefully these examples helped. If you have questions, comments, leave them in the comment box. If not, I will see you guys in class. Thanks, everyone.